Hello, good morning, good afternoon, and good evening, Sir Ramon Garcia. I'm Carlos Vincent Fernandez, and welcome to my video project presentation. So in this video project presentation, I will discuss and simulate the MOSFET amplifier circuit. So what is MOSFET? MOSFET is also known as metal oxide semiconductor field effect transistor. It is a type of semiconductor device transistor that is widely used for switching purposes and for the amplification of electronic signals in electronic devices. It has a 4 terminal devices having drain, gate, source, and body terminals. Actually, it has a 4 terminals, but we only use 3 terminal devices. So the one is called body terminals, also known as substrate, is for the use of output connection and for the ground terminals. There are two types of MOSFET. One is the depletion mode. Depletion mode, no voltage across the gate terminal, but the channel shows its maximum conductance. And the voltage across the gate terminal is either positive or negative. Then the channel conductivity decreases. So in other words, it is like to be a normal closed switch. This means that to apply voltage to the gate, to the source, to turn off the MOSFET to allow the current to pass. So depletion mode has two channel types. One is the N-type channel and second is P-type channel. N-type channel is the arrow is going into the gate, while the P channel is the arrow is going out from the gate. So the second type of MOSFET is called enhancement mode. Enhancement mode, when there is no voltage across the gate terminal, then the device does not conduct. When there is a maximum voltage across the gate terminal, then the device shows enhanced conductivity. So in other words, enhancement type is the opposite of depletion type mode. Enhancement types are like the normal open circuit. This means to apply the voltage to the gate, to the source, to turn on the MOSFET. So just like in depletion mode, it has two channels, namely N channel and P channel. N channel has the arrow is going into the gate, while the P channel has going out from the gate. So compared to the depletion mode, it has a closed straight lines, while in this enhancement mode has a broken lines. So before I proceed to the simulation, I use the N channel, this one, N-type channel MOSFET enhancement mode. So in this slide is that this circuit I created called MOSFET amplifier circuit. So I use it as a common source amplifier. So let's proceed to the simulation in LTSpice to get the parameters. So here is the circuit that I created here in LTSpice. So this is the MOSFET amplifier circuit that I created. So this type of common amplifier is known as the common source amplifier. So next is also it has a voltage divider bias circuit because it has resistor that parallel to each other. So R1 is a parallel of R2, RD is the parallel of RS. Next is V2 is the drain voltage, and this one is the V1 is the input signal, VIN is a voltage input, and V out is the voltage output. Next, it has a 3 capacitor. So C1 has 1 micro, and C3 has a 1 micro also. Next, C2 is a bypass capacitor. It has a 100 micro. So lastly is this, I forgot that RL is the load resistance. So here is the M1. M1 is the MOSFET transistor. It is a N-channel enhancement mode. So before we using the SPICE directive and type the OP, first is to modify first the M1 MOSFET transistor. So I put here the 1 and 100. So now I modify the MOSFET transistor. So type OP. So here's the OP right now, and click run. So as you can see here, it has a voltage input of 0. The voltage gate is 2.37. VN001 is 15. VN001 is, I think it is from nodes. I think it is from nodes. From this one, I think this is VN001 or near the ground. VD is the drain voltage is 11.5. VS is the source voltage 1.04. V out here is the 5.75, 044E to negative 14. ID is the current drain. It has a 1.75. IG is also 0, same as in the voltage input. IB is the current base. It has a negative 1.04611E to negative 11. IS is a current source. It in M1 in MOSFET, so 0.175, negative 1.75 milli. IC3, C3 is 1 micro, 1.15009E to negative 17. C2 is the bypass capacitor, so 1.04974E to negative 16. And C1 is the near from voltage input is 2.37245E to negative 18. So R1, the current of R1 here is the 1.15009E to negative 17. So next is RS. RS is here the source resistor. It has a 1.75 milli. RD is here. The current here is the 1 also is 1.75 also. R2 here is the, so it has a 382.65 micro, and R1 is also the same 382.65 micro. Next, the current in V2 here, the 15 volts is, it has a negative 2.13, and the V1 here, the current in V1 here is 2.37245E to negative 18. So let's copy and put here. Okay, so I think I will put here. Next is to measure the transient. So tran 0, 10, M, and 0. So I will remove the OP. So I click run again. So I will put here the graph of, So add the plot plane, add plot plane, add plot plane, add plot plane once. So I will put here the phases of the voltage input signal, then add traces of voltage output signal. Next is to add the voltage drain, voltage gate, and lastly is the voltage source. Oh, so different. So here VIN is it has a 180 degrees of wave, and also it is same as in VD is the voltage drain. It is same as in voltage. I'm sorry. Voltage input is same as in the gate because it is near to each other, VG and VN. Next is the Vout, which is the voltage output is the same as in voltage drain because it has also inverted in 180 degrees. So here RD and VD and Vout, because they are same, they are near to each other. Well, the only difference here is the VS, so the voltage source. As you can see here is it has also it has same as in other waveforms of VIN, VIOut, VD, and VG. It has a 180 degrees. However, it moves down. As you can see, it moves down. So from here, it's near. It is near here. It is here. Then after wave and travel until it's going down. So next is to estimate the voltage peak to peak. So first, this is for rough estimation first only. So I will remove this delete display, and I will use voltage input signal. So cursor 1 here, and cursor 2 is here. Oops, sorry. So as you can see here, it has a negative 19.974,078 millivolts. Okay. So I will use, since it has a negative 19 milli, so now we will use the parameters. So to measure the peak-to-peak voltage and the output voltage input peak-to-peak and voltage output peak-to-peak. So using this SPICE directive is to dot MES. So MES is VI and PP, voltage input signal peak to peak. So next is PP, it is peak to peak, So V, peak to peak value of V, voltage VIN, which is here. Oops, here. Okay, so now, yeah. Next is, this is where to find the voltage input here. So voltage input signal. Next is to enter again. Control M. Measure of V out PP. So peak to peak. V out. Next is that MAS. So that's the V out PP, which means the voltage output here, peak to peak. So next is to AV. AV is the voltage gain. So to get the voltage gain is to that MEAS measure. AV is the voltage gain param. So it's to V out PP divided by DINPP. So here I put here now. So click or run again. So spice error log. So as you can see here, it has VINPP, PP, peak to peak value of voltage input has a 19.9983 milli. So it is same as in the rough estimation. Next is voltage output peak to peak. It has a 0.77.08. Okay, 77.09 milli. So that's the voltage output peak to peak. Next is the AV. AV is the voltage gain. So I divide it to get the voltage gain is to divide the voltage output peak to peak divided by voltage input peak to peak. So here I will highlight this and I put it in text to remember. So yeah, that's the, so I will have anyway space like that. So here is now the result. I mean the measured value. Next is to measure the current gain. So here is about the voltage gain. Now we will measure now the current gain. So .MEAS measure. I is the current, IN, which means the current input signal. EP, peak to peak, I C1. C1 is here, so we will measure here the voltage input current input peak to peak, IC1. So control M again. That MEAS. So in current output peak to peak, so I D. So which I should measure is the M1. M1 is the MOSFET transistor, so M1. So next, the ID of M1, so which means that ID is the current drain of MOSFET transistor. So control M again, so that MEAS is AI. AI is a current gain. So parameter, so param, so I out, it is same as in the function of voltage gain, but it is in current. So since voltage gain is V out divided by V out peak to peak divided by VI and voltage input peak to peak, while here in the current gain is that MEAS AI. AI is the current gain, param I output, which is the current output, divided by IIN, which is the current input. So let's enter. So I will put in the top. So I will run again. So spice error log. So as you can see here, it has the current of the peak to peak voltage, peak to peak current input is 3.86658 E to negative 6, so which means 3.867 microamps. So the next is the I out, which is the current output from the current drain in M1 is the MOSFET transistor. So 53.46 microamps. So therefore the AI it is a current gain equals to 13.8269. So or 13.83. So copy and paste here. So we have now the value of the current input, current output, and the current gain. So next is to measure the power gain. So dot MEAS AP. AP is the power gain. So to get the power gain is to AP param AI multiplied by AV. So we know that power equals to voltage times the current. So when we apply to find the power gain is to multiply the current gain multiplied by voltage gain. So okay, I click here. So run again. Spice error log. So we have 53.2991 watts. So highlighted. So I will paste here. So that's the power gain. So next, so the next is to find the input frequency and the output frequency. So next is to use the spice directives. So dot MEAS. So T1 is the T sub 1 should be. So T1 equal find time when VIN equals to 0.5 M, which is the time. So control M again. That MEAS T2 find time when V out equals to 0.5 M with cross equals to 3. Next is MES to find the input frequency. So param 1 divided by T2 minus C1. So we know that frequency is equals to 1 over T. T is the time. So to find the frequency of this amplifier is to 1 over T2 minus T1, it is the time. So 1 over T is the equal to frequency. So next is to find the voltage output. So again, so I change it from T1 to TA to prevent the error in spice error log. Because if I T1 here, if I set this T1 here and then T1 here, then this will get the cause error in spice error log. So TA, so 1.5 instead of 0.5, I changed it to 1.5 milli. So I changed here is the out. Oops, I'm sorry. For correction, in T2 I will change in VIN. Sorry, because this part is about the input frequency. So next is measure TB instead of T2. So I change it to TB. So V out 1.5 cross 3. Next is I change here in frequency out, F out, which means the frequency output, param 1 divided by T2 minus T1. Again, so frequency equals to 1 over T. So this part of T2 minus T1 is the time. So I click OK. Then I will put here. So I click run again. And let's spice error log. So where is it? Ito. This one is T1, it has a 7.94 micro. T2 is 1.00 milli. So the frequency input, it has a 999.981. So it has, the frequency input is 999.981, while here is time is 489.13 micro, and next is 1.49 milli. So now the frequency output is 999.981, which is same as, so therefore frequency input equals to frequency output equals to 999.981 Hertz. So let's copy again. So here is here. I'll put here. So now, oops, I hide something. Yeah. So now we got the results of the parameters in this circuit. So in conclusion, this type of FNT amplifier. It is a MOSFET amplifier circuit that provides a good overall performance configuration. As such, it is often thought as the most widely used configuration. So which means that this circuit was popular configuration in some electronic devices like that. So we find out the parameters. So the voltage in, the voltage of each component. So I found the value of the current of each component, and I find out the peak-to-peak value of voltage and the current, and also the voltage gain, current gain, and the power gain. And then I found the value of frequency input, the input frequency and the frequency output. So that's the end of this demonstration of the MOSFET amplifier circuit common source amplifier. So let's go back to the PowerPoint presentation. So after the simulation, here are the advantages and disadvantages of MOSFET. So the advantages is MOSFET provides greater efficiency while operating at lower voltages. And the absence of gate current results in high input impedance, producing high switching speed due to lower resistance of the channel. And they operate at lower power and draws no current. While the drawbacks or the disadvantages is it has a short life. MOSFET is very sensitive when it comes to fragile, in which it is vulnerable to electrostatic damage during installation. And lastly, it is very susceptible to overload voltages. So since MOSFET is very efficient type of transistor, but it has some short life, or it is very sensitive transistor. So before we end of this video project presentation, here are the reference. So that's all for today for MOSFET amplifier circuit discussion. Once again, I'm Vincent U. Fernandez, section of B18 from course of ECEA101L. Thanks for watching and have a great day.